He was born on June 13, 1831 in the heart of Edinburgh, Scotland, a city of cold wind stone towers and candlelit studies where scholars and poets often crossed paths. From the beginning, James Clerk Maxwell seemed to belong to a different rhythm of existence, as though his young eyes saw patterns where others only saw chaos. His father, John Clerk Maxwell, was a lawyer by profession but an engineer at heart, a man who loved to tinker with machines and structures on the family's estate, Glenlair, in the rolling hills of Galloway. His mother, Frances Kay, came from a family with a strong scientific tradition. From her, the boy inherited not only intelligence but also curiosity, a hunger to understand the why behind every flicker of light and every twist of motion. In the early years of his life, Maxwell was drawn to the world's hidden designs. As other children played with toys, he played with geometry. He would trace shapes in the dirt, draw circles with string, and ask questions that startled adults with their depth. But why does the shadow change shape? He would ask when the sun shifted behind clouds. Why does the water shimmer when I throw a pebble? These were not idle childhood questions. They were the first stirrings of a mind destined to see the unseen, to measure the immeasurable. His mother, recognizing this spark, took charge of his early education. She didn't believe in rote learning, she believed in nurturing wonder. She taught him scripture and science side by side, for she believed that understanding the laws of nature was another way of appreciating creation itself. By the age of 8, young James was already fascinated by geometry, light, and the way colors blended in sunlight. He would spend hours experimenting with spinning tops painted in different hues, watching how the colors merged when the top whirled, an early fascination that would later mature into his groundbreaking studies on color perception and the electromagnetic spectrum. When his mother passed away from cancer when he was just 8 years old, it was a wound that cut deeply into his gentle spirit. The laughter in the house grew quieter, and his world became lonelier. But perhaps that solitude drove him even further inward, into the silent world of thought and pattern. His father, now his main companion, encouraged him to explore his interests freely. The fields and rivers of Glenlair became his laboratory, stones, water, and light his instruments. The young boy would roam the countryside, building models of geometric figures using bits of wire, thread, and wood. He was not merely playing. He was learning to see order in nature's apparent randomness. In his notebooks, some of which still survive, we find the seeds of the mathematical genius he would become. At the age of 14, he wrote his first scientific paper, titled On the Description of Oval Curves, in which he described a method of drawing complex geometric shapes using string and pins. It was a remarkable piece of work for someone so young, precise, logical, and beautifully constructed. When he presented it to the Royal Society of Edinburgh, he was too young to deliver it himself, so his tutor read it aloud to the audience. The scholars present were astonished. They knew they were witnessing the emergence of a rare intellect, a boy who could see geometry not as mere lines and angles, but as a living language that described the architecture of the universe. Even at that age, Maxwell had a peculiar habit. He would never be satisfied with surface answers. When asked a question, he would often pause, look into the distance, and then respond with layers of reasoning, as if he were tracing the invisible threads connecting every idea. His mind was not quick in the ordinary sense, it was deep, methodical, and reflective. He saw every problem from multiple perspectives, a trait that would later allow him to unify seemingly disconnected forces into a single elegant theory. At Edinburgh Academy, where he went to study at age 10, Maxwell stood out as both brilliant and awkward. His country accent and unpolished manner made him an easy target for ridicule among his classmates, many of whom came from more refined urban families. But beneath the teasing, there was also admiration. When others struggled with arithmetic, he played with it. When others memorized geometric theorems, he discovered new ones. He once told his teacher that he loved to find out how things are done and why they are so. That phrase, simple yet profound, was the core of his entire life philosophy. His notebooks from those school years are filled with experiments, sketches, and equations that reveal a restless curiosity. He built sundials and tried to calculate the motion of the planets. He dissected flowers to study symmetry. He drew color wheels and wondered why the rainbow always appeared in the same sequence. He questioned why iron filings aligned themselves around a magnet. These were not just playful diversions. They were the early echoes of the grand questions he would later solve as an adult scientist. He was, even as a child, building a bridge between observation and abstraction, between the physical and the mathematical. It is often said that Maxwell had a unique ability to think in pictures, to visualize complex ideas as geometric forms or dynamic movements. In his later life, this visual imagination became the foundation of his scientific breakthroughs. But even in his childhood, the world was a moving diagram to him. When he watched ripples spreading across a pond, he imagined invisible waves carrying energy. When he saw a spinning wheel, he saw rotational symmetry. This ability to see through the surface of things was what set him apart. He did not merely look, he understood. His father's estate at Glenlair played a quiet but crucial role in shaping this perspective. The wide skies, the rivers, the play of light over hills, all of it became a kind of living classroom. James would experiment with lenses and mirrors, studying how light reflected and refracted. He loved to observe soap bubbles, fascinated by their iridescent colors, trying to understand the physics behind their shimmering skins. Later, he would explain the phenomenon of color mixing in a way that paved the path toward the modern RGB color model, the foundation of digital screens today. But in those early days, he was simply a boy watching the dance of light with endless wonder. Maxwell's fascination with mathematics grew naturally from his fascination with nature. To him, math was not abstract, it was the hidden structure of reality. While most students saw mathematics as a set of rigid rules, Maxwell saw it as music, a language that expressed the harmony of existence. The curve of a bird's flight, the spiral of a shell, the vibration of a string, all of it could be translated into numbers and equations. He once wrote that mathematics is the only true poetry, and in his mind, every formula was a verse describing creation's beauty. By his teenage years, his talents were too great to be contained within the small academy walls. He began attending lectures at the University of Edinburgh at just 16, where he studied natural philosophy, mathematics, and logic. There, he was introduced to the works of great thinkers like Newton, Descartes, and Faraday. Newton had shown that the motion of planets could be described by simple mathematical laws. Faraday had demonstrated that electricity and magnetism could produce motion and energy. But for Maxwell, these were not just discoveries, they were clues, fragments of a grander pattern waiting to be revealed. He felt that beneath all these laws lay a deeper unity, something that connected light, magnetism, and motion through mathematical relationships. That feeling, that intuition, would become his life's guiding vision. Even in those early years, he had a remarkable sense of humility and humor. He never took himself too seriously, and though his ideas were often far beyond his peers, he remained gentle and approachable. He enjoyed reciting poetry, singing Scottish folk songs, and drawing caricatures of his professors. His laughter was genuine, but his eyes always seemed to be contemplating something beyond the visible world. To his friends, he was both a dreamer and a logician, a man of imagination and discipline combined in rare balance. His deep fascination with light and color continued to evolve. He performed experiments using colored filters and spinning discs to study how the human eye perceives combinations of primary colors. These studies would later lead him to formulate the first true theory of color vision, and even to create the world's first color photograph, a milestone that stemmed directly from the curiosity of his boyhood. It was as if every question he asked as a child was waiting patiently to find its answer in his adult years. The beauty of Maxwell's mind lay not only in its brilliance, but in its unity. He did not separate emotion from reason or imagination from calculation. For him, science was a kind of spiritual pursuit, a quest to see the divine order within the apparent disorder of nature. When he derived equations or constructed geometric models, he was, in a sense, composing music, a harmony that existed between thought and reality. His later equations of electromagnetism were not born suddenly. They were the inevitable flowering of this lifelong pursuit of pattern and meaning. In those quiet Scottish landscapes where he grew up, surrounded by fields and streams, he found not isolation but inspiration. Nature itself became his tutor. Every wave, every beam of light, every shadow on the water seemed to whisper mathematical truths. He once wrote that the goal of science was not to invent explanations, but to discover the harmonies already written into the universe. That belief began forming in his childhood when he first noticed that beauty and logic were not opposites but reflections of one another. As he matured, this way of seeing, this blending of observation and abstraction, became his defining gift. He could imagine invisible phenomena in visual terms and then express them in precise mathematical symbols. That rare dual ability, to visualize like an artist and calculate like a mathematician, was what allowed him to make the leap from seeing patterns to discovering the fundamental laws of electromagnetism decades later. Maxwell's early fascination with mathematics was not about numbers alone. It was about meaning. Every equation was a doorway into the hidden architecture of the cosmos. Every pattern he saw was a promise that something deeper was waiting to be understood. This mindset made him different from the scientific minds of his time. Where others sought control over nature, he sought communion with it. Where others tried to isolate phenomena, he sought to unify them. His equations would one day show that electric and magnetic fields were not two separate entities, but one continuous field, a field that vibrates through space as light itself. But that unifying vision began long before he could write down a single equation. It began with a boy staring into a pond, watching ripples spread, and wondering what laws governed their motion. His early years were, in many ways, a preparation for the revelation he would later bring to the world. The precision of his geometry, the sensitivity of his color studies, the curiosity that led him to ask impossible questions. All these were the early movements in the great symphony of his life. His fascination with mathematics gave him the tools, his wonder gave him the purpose. Together, they shaped the mind that would later rewrite humanity's understanding of the universe. Maxwell once remarked that thoroughly conscious ignorance is the prelude to every real advance in knowledge. Even as a child, he embraced not knowing as the beginning of discovery. He would stare at a puzzle of nature, a reflection, a shadow, a motion, and instead of being frustrated by its mystery, he would be delighted by it. He loved questions more than answers, because he believed every answer was just another doorway to deeper mysteries. That endless curiosity, the joy of exploring, of connecting, of finding patterns, was the essence of James Clerk Maxwell's early genius. It was the light that guided him from the quiet hills of Glenlair to the foundations of modern physics. The young James Clerk Maxwell grew in a world that was changing rapidly, a century of invention, steam power, and scientific revolution. Yet, in the midst of that noisy progress, his genius remained quiet and introspective. He preferred the solitude of thought to the applause of recognition. As he grew older, his understanding of mathematics deepened into something almost spiritual, not merely a subject to study, but a way of seeing reality. To Maxwell, the laws of nature were not created by man. They were eternal, waiting to be discovered by anyone who could read the hidden script of the universe. And for him, that script was written in the language of equations. When he entered the University of Edinburgh, the world around him expanded. The great lecture halls and libraries exposed him to the writings of the ancient mathematicians, Euclid, Archimedes, and Newton, whose ideas had built the foundation of science. But even among such monumental thinkers, Maxwell's mind sought connections they could not see. Newton had unified motion and gravity. Maxwell longed to do the same for electricity, magnetism, and light. The idea was still vague, forming somewhere deep in his imagination, but its roots stretched back to his earliest experiences with pattern and form. The world, he believed, was not a collection of separate parts, but a grand system of relationships, and mathematics was the only tool capable of expressing that unity. In the evenings, after lectures, he would retreat to his small study room lit by a single oil lamp. The faint light would flicker across his papers, filled with sketches of geometrical figures and complex formulas. Sometimes he would pause, look up, and smile quietly, as though he had just glimpsed a piece of a larger truth. His friends often described him as absent-minded, lost in thought even during casual conversation. But that absent-mindedness was not distraction, it was absorption. Maxwell's thoughts were constantly moving through layers of abstraction, weaving together geometry, physics, and intuition into something no one else could yet see. It is said that true genius lies not in knowing everything, but in seeing connections where others see divisions. Maxwell possessed that rare gift in abundance. To him, an electric current flowing through a wire was not just a physical phenomenon. It was a moving pattern of energy. A magnetic field was not an invisible force, but a geometry in motion. Even light, the most mysterious of all, was, to his mind, a rhythmic oscillation in an invisible medium, something that could be described with precision if only one found the right mathematical form. These were thoughts far ahead of his time, but even as a young man, his imagination had already begun to shape the equations that would later define the modern world. His professors recognized his brilliance, though some found his methods unusual. While most students approached problems step by step, Maxwell often jumped directly to the heart of a concept, sketching curves and waves to illustrate ideas that had not yet been formally proven. This ability to visualize the invisible, to turn abstract theory into tangible imagery, was one of his greatest strengths. In his mind, every equation had shape and motion, every line of algebra a rhythm. He did not merely solve problems, he saw them unfold like living structures. By the time he left Edinburgh for Cambridge University, Maxwell was already a name whispered with admiration in academic circles. Cambridge, with its centuries-old tradition of mathematical excellence, became the perfect crucible for his developing ideas. There he met some of the brightest minds of the time, men who would later shape physics, astronomy, and engineering. Yet, even among them, Maxwell's intellect stood apart. He excelled not only in mathematics but in philosophy and poetry, a rare combination that gave his thinking both rigor and depth. To him, the boundaries between disciplines were artificial, truth was one, and it could be approached from many directions. At Cambridge, he was drawn deeply into the world of geometry and mechanics, but it was the study of electricity and magnetism that began to consume his imagination. The experiments of Michael Faraday fascinated him beyond measure. Faraday, who had little formal education, had discovered that electric currents could produce magnetic fields and that changing magnetic fields could generate electricity. But Faraday's ideas were visual and experimental. He spoke of lines of force, invisible threads connecting charges and magnets through space. Many mathematicians dismissed these as vague and unscientific. Maxwell did not. He saw in Faraday's intuition a truth that needed only the structure of mathematics to reveal its full beauty. This was the moment when his lifelong fascination with patterns found its ultimate purpose: to give mathematical form to the invisible architecture of the universe. His childhood obsession with geometry, symmetry, and waves now converged into one vision. He imagined space filled not with emptiness, but with continuous fields, invisible patterns of energy stretching from one point to another, influencing everything they touched. These fields, he reasoned, could be described by a set of equations that would later become the foundation of electromagnetism. In these moments of realization, Maxwell's years of silent observation and playful curiosity found meaning. The boy who once traced curves with strings and pins had grown into the man who could describe the dance of light itself through the language of mathematics. Maxwell's creative process was unlike that of most scientists. He did not build theories from experiment alone. He built them from intuition and imagination, and then used mathematics to test their truth. He believed that the universe was logical because it was beautiful, that the laws of nature were elegant because nature herself was a reflection of order. In one of his letters, he wrote that the goal of science was to connect by accurate law those quantities which are already known. This idea of connecting, of unifying, ran through everything he did. It was not enough for him to know how something worked. He wanted to understand why it worked that way and how it related to everything else. Yet even with his extraordinary mind, Maxwell remained humble and kind. He did not seek fame or recognition, he sought understanding. Those who met him described him as gentle, cheerful, and deeply thoughtful. He had a quiet humor that made people feel at ease, and though he spoke with great intelligence, there was never arrogance in his tone. This humility was not false modesty. It was a reflection of his belief that truth belonged to no one person. Knowledge, in his view, was a shared journey, a collective effort of humanity reaching toward the infinite. His early fascination with patterns continued to shape his thinking in unexpected ways. For example, he became deeply interested in how gases behave, a problem that had puzzled scientists for decades. By applying statistical methods to the movement of gas molecules, he developed the Maxwell-Boltzmann distribution, a cornerstone of statistical physics. This idea, like all his others, came from his way of seeing order within apparent randomness. To him, even chaos had structure if one only knew how to look for it. The thread connecting all these discoveries was his childhood gift. The ability to see mathematical beauty in everything. Whether it was the curve of a line, the vibration of light, or the invisible pull of magnetic fields, Maxwell perceived all as expressions of a deeper order. He often compared science to art, saying that both sought harmony and form. His mathematical equations were not dry symbols, they were brushstrokes in a grand cosmic painting, each representing motion, energy, and connection. In his later years, when he finally formulated his four famous equations, the ones that unified electricity, magnetism, and light, he did so with the same playful curiosity that had guided him since childhood. He did not claim to have invented these laws, he said he had merely discovered what was already there. To him, the universe was like a vast symphony, and his equations were the notes written into its score. When those equations were finally published, they transformed the very foundations of physics, leading to everything from radio waves to modern communication technology. But to understand how Maxwell could reach such profound truths, one must return to his early fascination with patterns, for that was where it all began. The boy who had once stared at the ripples on a pond had learned, in time, to describe how energy ripples through space. The same curiosity that led him to trace shapes with a string became the method through which he traced the invisible lines of electromagnetic force. His imagination had trained him to see beyond the limits of the senses, to visualize the movement of invisible fields as clearly as one might see waves of water. It was that visual, pattern-oriented thinking that allowed him to make the leap from the tangible to the abstract, from play to principle, from geometry to physics. What makes Maxwell's story so remarkable is how human it is. His genius was not the cold brilliance of calculation alone. It was warm, creative, and profoundly empathetic. He saw beauty where others saw complexity, and he approached knowledge not as conquest but as communion. In his eyes, the universe was not a machine to be mastered but a mystery to be understood. This emotional intelligence, fused with mathematical mastery, gave his work an enduring humanity. His equations describe not just forces and fields, but the deep interconnection of all things, a concept that still echoes in modern science. By the time of his early death in 1879, at the age of just 48, Maxwell had already changed the course of physics forever. Yet the roots of his genius, the source of his insight, lay not in the laboratories of Cambridge, but in the quiet fields of his childhood, where a curious boy once played with strings and mirrors, searching for patterns in the light. Every discovery he made as a man was an answer to a question he had first asked as a child. How do things connect? Why do they move as they do? What is the hidden harmony behind the noise of nature? Those questions guided his entire life. Even now, more than a century later, his influence continues to shape the world. Every radio signal, every wireless transmission, every beam of light passing through a fiber optic cable owes its existence to the vision that began in Maxwell's young mind. And yet, perhaps his greatest gift was not technological but philosophical. The idea that knowledge and beauty are not separate pursuits but two sides of the same truth. He showed humanity that the universe, when seen through the lens of mathematics, is not cold or indifferent but full of order and grace. In the end, Maxwell's early fascination with patterns and mathematics was not simply a childhood talent. It was the foundation of a worldview. It taught him that behind every form lies function, behind every motion lies law, and behind every law lies meaning. He learned to see the world as a single, unified system, a tapestry of interwoven forces, each governed by precise mathematical harmony. That vision shaped every discovery he made and continues to inspire scientists today. There is something deeply poetic about the way Maxwell's life came full circle. The child who loved the colors of light grew up to reveal that light itself was a wave of electricity and magnetism intertwined. The boy who marveled at geometric shapes became the man who described the geometry of space and fields. The student who admired Faraday's invisible lines of force became the mathematician who proved they were real. Every moment of wonder in his early life became a step toward uncovering the profound unity of nature. When we think of Maxwell now, we remember not only his equations but his way of seeing. He saw the universe as something living, structured, and purposeful, a place where beauty and logic met. His childhood fascination with patterns was more than curiosity, it was a calling, a whisper from the universe inviting him to decode its secrets. And in answering that call, he gave humanity one of its greatest intellectual treasures, the realization that everything we see, touch, or feel is part of one continuous, interconnected field of energy. James Clerk Maxwell's journey from the curious boy at Glenlair to the architect of modern physics is a testament to the power of wonder. His childhood love of patterns was not just a phase, it was the foundation of his genius. He showed the world that true understanding begins with curiosity, that even the smallest question can lead to the greatest revelation, and that mathematics, when guided by imagination, becomes not just a tool for measurement, but a bridge to the heart of the universe. And so, the story of Maxwell's early fascination with patterns and mathematics is not merely the story of a prodigy. It is the story of how one mind learned to listen to the music of the cosmos, and to write it down in the timeless language of equations. In the heart of the 19th century, when science was divided into separate kingdoms, electricity on one side, magnetism on the other, and light standing apart as a mystery of its own, there came a man who dared to imagine that all these forces were, in truth, one. His name was James Clerk Maxwell. The world knew of electricity, the spark that could shock or illuminate. It knew of magnetism, the invisible pull that guided compasses and moved iron. It knew of light, the ethereal wave that painted the sky and gave life to the earth. But no one could see the thread connecting them. Maxwell did. To him, the universe was not a collection of disconnected phenomena. It was a grand, continuous field of motion and energy, woven together by mathematical law. The story of how he discovered that unity begins not in a laboratory full of instruments, but in the quiet depths of thought. Maxwell was a thinker who saw equations as living things. He could look at an experiment, the swinging of a magnet near a coil of wire, the flicker of an electric current, and visualize not just the physical motion, but the invisible waves of energy that moved through space around it. This ability to imagine what could not be seen was his greatest gift, and it allowed him to bring together ideas that had long remained apart. At that time, Michael Faraday's work had already transformed the scientific world. Faraday, a self-taught experimentalist with an extraordinary intuition, had discovered that moving a magnet near a coil of wire could produce electricity, a process known as electromagnetic induction. He had also shown that electric currents could create magnetic fields, and that magnetism itself could induce motion. Yet, for all his genius, Faraday lacked the language of mathematics to express these phenomena precisely. He spoke of lines of force, invisible structures that carried energy through space. But many of his contemporaries dismissed these as vague metaphors. They wanted numbers, not images, formulas, not imagination. Maxwell, however, saw something different. He understood that Faraday's lines of force were not metaphors but realities. He believed they could be described mathematically, and that the entire behavior of electricity and magnetism could be captured in equations, elegant, universal, and exact. Where others saw confusion, Maxwell saw a pattern waiting to be revealed. He began his quest by asking a simple but profound question: what happens in the space around an electric charge or a magnet? Scientists before him treated that space as empty, a void through which forces acted at a distance. But to Maxwell, the idea of action at a distance made no sense. He believed that if forces existed between objects, something must exist in the space between them to carry those forces. This something was what Faraday had called the electromagnetic field, an invisible medium filling all of space. Maxwell decided to treat this field not as a vague concept but as a real, physical entity with its own dynamics, tensions, and motions. In his study at Cambridge, surrounded by papers covered with symbols and sketches, he began to construct the mathematical structure of this field. He imagined space filled with lines of energy, stretching and twisting whenever electricity or magnetism appeared. He treated these lines like elastic strings, capable of storing and transmitting energy. If you moved an electric charge, the surrounding field would change shape, producing a ripple that spread outward, much like waves on a pond. Those ripples, Maxwell realized, might be the key to understanding light itself. But before he could reach that revelation, he had to solve the problem of how electricity and magnetism were related. He knew from Faraday's experiments that a changing magnetic field could produce an electric current. But could the reverse also be true? Could a changing electric field create a magnetic one? It was a daring thought, and one that no experiment had yet proven. Still, Maxwell's intuition told him it must be so. If symmetry governed nature, as his mathematics suggested, then electric and magnetic effects must be mirror images of one another. He added a new term, the displacement current, to the existing equations that described electricity. This idea, though abstract, turned out to be revolutionary. It implied that even in empty space an electric field could give rise to a magnetic field, and vice versa. This completed the circle. Electricity could create magnetism, and magnetism could create electricity. The two forces were no longer separate, they were aspects of a single phenomenon. For the first time in human history, electromagnetism was born as a unified theory. In his 1861 paper, On Physical Lines of Force, Maxwell presented his vision to the world. The equations were complex, but their meaning was breathtaking. They described not just how electricity and magnetism interacted, but how they moved together through space as waves. According to the mathematics, these waves traveled at a specific speed, a speed Maxwell calculated using measurements of electric and magnetic constants. When he compared that value to the known speed of light, he realized they were the same. The conclusion was inescapable. Light itself was an electromagnetic wave, a vibration in the electromagnetic field. The glow of the sun, the colors of the rainbow, the flicker of a candle, all were manifestations of the same forces that produced electricity and magnetism. It was one of the greatest unifications in the history of science. To appreciate the magnitude of that discovery, One must remember what it meant in its time. For centuries, light had been one of nature's greatest mysteries. Was it made of particles, as Newton believed, or was it a wave, as Huygens proposed? Experiments had supported the wave theory, but no one knew what the waves were made of. What exactly was waving? Maxwell's equations gave the answer. What vibrated was the electromagnetic field itself. Light was not a separate substance. It was electricity and magnetism in motion, bound together in perfect harmony. This realization changed everything. It meant that light, electricity, and magnetism were not three distinct domains, but different expressions of one universal field. It also implied that there could be waves of electromagnetism that the human eye could not see. Waves longer or shorter than visible light. Decades later, Heinrich Hertz would confirm this prediction by generating radio waves in the laboratory, proving that Maxwell's vision was correct. The invisible web of electromagnetic energy he described would go on to shape every aspect of modern life, from radio and television to radar, microwaves, and wireless communication. But long before those technologies existed, Maxwell's imagination had already traveled there. He had glimpsed a universe alive with waves and fields, an interconnected whole where energy flowed continuously through space. This was not just a scientific theory, it was a new way of seeing reality. For the first time, humanity could understand that the empty space between objects was not empty at all. It was filled with invisible fields, pulsing with energy and structure. Maxwell's path to this understanding was not without difficulty. His work was often misunderstood or overlooked during his lifetime. The mathematical complexity of his equations made them inaccessible to most physicists of the day. Some dismissed his field as a mere abstraction, something with no physical meaning. But Maxwell knew that truth does not always reveal itself in simplicity. He trusted the logic of his mathematics, believing that if the equations were beautiful, they must also be true. His faith in the harmony of nature guided him when others doubted. His creative process was unlike that of any scientist before him. He didn't separate intuition from analysis. He would often begin by visualizing a system, seeing in his mind the twisting lines of force, the flow of energy, the dance of electric and magnetic fields, and only afterward translate that image into mathematical form. This approach made his work deeply original, but it also set him apart from his contemporaries. To many, his theories seemed too abstract, too dependent on imagination. Yet history would prove that imagination, when paired with reason, can reveal the deepest truths of all. Behind every line of mathematics lay an image in Maxwell's mind, fields stretching across the universe like invisible threads, vibrating with the pulse of creation itself. His equations did not merely describe how electricity and magnetism behave, they revealed how nature communicates, how energy moves, interacts, and becomes light. It was as if he had uncovered the language of the cosmos, a set of symbols through which the universe itself speaks. In 1864, when Maxwell presented his paper, A Dynamical Theory of the Electromagnetic Field, he summarized his vision in a few profound sentences. The agreement of the results seems to show that light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. These words quietly marked a turning point in human understanding. What had once seemed like separate forces were now known to be one continuous phenomenon. The boundary between physics and light, between mechanics and optics, between the visible and the invisible, all dissolved in that unification. The implications of this discovery rippled far beyond physics. Maxwell's unification of electricity and magnetism created a new worldview, one that replaced the notion of isolated objects and empty space with an interconnected web of energy. It introduced the concept of fields, which would later become central not only to electromagnetism, but to all modern physics, including Einstein's theory of relativity and the quantum field theories that describe the subatomic world. Without Maxwell's equations, there would be no modern communication, no understanding of electromagnetic radiation, no foundation for the technologies that define the present age. What made Maxwell's achievement even more astonishing was that it came not from elaborate machinery or advanced instruments, but from thought itself. With little more than paper, ink, and imagination, he uncovered the hidden unity of nature, a unity that had escaped even the greatest minds before him. His equations were not simply calculations, they were a revelation of order in the universe. And yet, for all their power, he approached them with humility. He once said that his goal was not to impose theories on nature, but to discover what is already there. In his view, the laws of the universe existed independent of human thought. The task of science was simply to recognize and describe them. To truly grasp the wonder of Maxwell's discovery, one must imagine the invisible made visible. Picture a charge moving through space, surrounded by lines of force that twist and curl like unseen threads. As that charge accelerates, the lines begin to vibrate, sending ripples through the field, ripples that travel outward at the speed of light. Those ripples are light itself, the same light that warms the earth, that glows in the stars, that fills the cosmos. What we call brightness, color, and radiation are all expressions of this same electromagnetic dance. And the choreography of that dance is written in Maxwell's equations. By unifying electricity and magnetism, Maxwell did more than solve a scientific puzzle. He gave humanity a new way to understand reality. He showed that nature's forces are not separate entities in competition, but harmonious expressions of a single truth. His equations, beautiful in their symmetry, profound in their meaning, became the bridge between classical and modern physics. They taught us that the universe is not static but dynamic, filled with waves and energy, constantly in motion. And so, the quiet Scottish mathematician who once studied the play of light and color in his childhood would go on to reveal that light itself was the pulse of the universe. His discovery of electromagnetism was not just a triumph of intellect, it was a triumph of vision. It showed that imagination, guided by mathematics, could illuminate the deepest structures of nature, connecting what had seemed forever separate. The revelation that electricity and magnetism were two faces of one grand phenomenon did not come to Maxwell in a single flash of inspiration. It unfolded like the slow opening of a cosmic flower. Once his equations were complete, he spent months re-examining every symbol, testing every assumption. He questioned whether the beauty he saw in the mathematics truly reflected nature or merely his imagination's desire for symmetry. But the deeper he explored, the more he realized that this harmony was not a human invention, it was woven into the structure of the universe itself. Maxwell's mind was restless. He saw in the interplay of electric and magnetic forces not just the mechanics of machines, but the poetry of creation. The field, that invisible ocean of energy filling space, became for him the very fabric of reality. To him, the cosmos was not an empty void but a living sea, vibrating with waves of light and energy. Every spark, every flicker of lightning, every beam of sunshine was part of a single universal rhythm. The equations he had written were its sheet music, and nature itself was the grand symphony performing it. He continued refining his theory in seclusion at Glenlair, his family estate in Scotland. The rolling hills and quiet streams around him provided the calm he needed to think. He would spend hours walking alone, tracing with his cane the imaginary curves of electric lines in the air, visualizing how they twisted and interlocked. In the evenings, he returned to his study, where candles burned late into the night over pages filled with dense mathematics. The fireplace glowed faintly while he whispered equations to himself, turning over in his mind the relationship between energy, motion, and light. Few could have guessed that in this lonely house, far from the great laboratories of Europe, a man was rewriting the very laws of the universe. When Maxwell finally published his full set of equations, what we now call Maxwell's equations, they were presented not as abstract symbols, but as a vision of how the universe breathes. They consisted of 4 elegant expressions describing how electric and magnetic fields are created, and how they influence one another. From these four relationships, every known electromagnetic phenomenon could be derived. Together, they told a story. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. When these two feed each other, they form a self-propagating wave, an electromagnetic wave, moving through space at the speed of light. This insight transformed physics into a new kind of language, one that described not just objects but fields, not just matter but the unseen energy that links all things. For centuries, scientists had built their understanding of nature on the idea of particles acting upon one another through direct contact or across empty space. Maxwell shattered that picture. He replaced it with a world where invisible fields filled every corner of the cosmos, mediating all interactions. Every atom, every charge, every magnet was merely a disturbance in this continuous medium. The boldness of this vision shocked his contemporaries. Some critics dismissed the notion of a physical field as metaphysical speculation. They preferred the certainty of mechanical models, gears, and levers, something they could see or imagine in familiar terms. But Maxwell's universe had no need for such analogies. In his equations, the field itself was real enough. It carried energy, momentum, and structure. The invisible had become tangible through mathematics. Slowly, others began to see what Maxwell saw. His theory predicted that electromagnetic waves should exist far beyond the range of visible light. Radio, infrared, ultraviolet, and more. It took nearly 25 years before technology caught up with theory. In the 1880s, Heinrich Hertz, a young German physicist, built an apparatus that generated oscillating electric currents. When sparks jumped between metal spheres, he detected ripples traveling through space, electromagnetic waves, just as Maxwell had foretold. Hertz's experiments became the experimental proof of Maxwell's vision. "It's just as Maxwell said," he declared. With that confirmation, Maxwell's dream leapt from mathematics into reality. The world was never the same. From those invisible waves would emerge radio, radar, television, the internet, and the entire wireless age. Every text sent, every broadcast transmitted, every satellite signal received is a living echo of Maxwell's insight. Yet he himself never saw any of it. By the time Hertz proved his theory, Maxwell had been dead for nearly a decade. He died in 1879 at only 48, his work appreciated by few and understood by even fewer. But the seeds he planted would grow into the technological civilization we now inhabit. Maxwell's unification of electricity and magnetism also laid the foundation for Einstein's special theory of relativity. Einstein later wrote that his own work was built on the shoulders of Maxwell. The constancy of the speed of light, a central postulate of relativity, was hidden in Maxwell's equations. When Einstein realized that light's speed was the same for all observers, regardless of motion, it was because Maxwell's mathematics demanded it. Thus, the bridge from classical to modern physics runs directly through Maxwell's mind. His field concept became the core of 20th century science, shaping everything from quantum theory to particle physics. But Maxwell's achievement was not purely intellectual, it was also deeply philosophical. He revealed that unity underlies diversity, that the apparent chaos of natural phenomena conceals a hidden order. Where earlier scientists saw separate domains, heat, magnetism, optics, Maxwell saw harmony. He once wrote, "All phenomena are connected by the same laws, and these laws reveal the unity of the Creator's plan." His faith in that unity guided his science. It gave him the courage to follow beauty even when the path was uncertain. The story of his discovery is, at its core, the story of how the human mind can reach beyond the senses. Maxwell never saw an electromagnetic wave. He deduced its existence through pure thought. He used mathematics not as a tool of calculation, but as a telescope of the mind, an instrument capable of revealing the invisible. Where a telescope extends sight, equations extend understanding. Through them, he saw the unseen universe, a universe of fields and forces stretching to infinity. Consider for a moment the human drama behind those equations. In the cold winter of 1864, Maxwell sat at his desk, weak from the illness that would later claim his life. Outside, snow covered the Scottish countryside. Inside, his study was silent except for the scratching of his pen. On that paper, he wrote lines that would outlive empires. Te tatem mare ar taptan zere a ta emai 88ab ta bigu 00 nutter 0 tae. They look like mere symbols, but behind them lies the pulse of creation. Electric fields curling into magnetic ones, magnetic fields birthing electric ones, forever intertwined. The simple elegance of those relationships spoke to a profound truth. Motion and change are the essence of the universe. Nothing stands still. Every point in space vibrates with potential. To grasp the magnitude of this insight, imagine the Earth itself as a tiny particle floating in a vast electromagnetic ocean. Sunlight reaching it is not a stream of particles striking its surface, but an oscillation of electric and magnetic fields traveling through the void. A wave journeying across 93 million miles of space. That same wave warms the soil, drives the winds, and fuels life. Maxwell's equations are what make that journey comprehensible. They are the invisible script of every sunrise. Yet for all the grandeur of his discoveries, Maxwell remained humble and quietly humorous. He often joked that his greatest achievement might be explaining color vision to artists rather than unifying the forces of nature. But deep down, he knew what he had done. He once confided to a friend that he believed his field theory would change how humanity perceived the cosmos. He was right. As time passed, physicists realized that his field equations were not merely accurate descriptions, but hints at deeper layers of reality. They contained within them the seeds of the quantum revolution. The idea that fields could vibrate, carry energy, and interact across space foreshadowed the quantum fields that would later describe electrons, photons, and every fundamental particle. In a sense, modern physics is an elaboration of Maxwell's idea that the universe is made not of solid matter but of fields and energy, endlessly fluctuating. Even today, more than a century and a half later, Maxwell's equations remain among the most beautiful expressions ever written. They are taught in every physics classroom, printed on spacecraft plaques, and etched into the minds of generations of scientists. Their beauty lies not only in their accuracy but in their simplicity. 4 equations that describe every electric and magnetic phenomenon in the universe, from the whisper of atoms to the roar of galaxies. To tell Maxwell's story is to tell the story of vision, the kind of vision that looks beyond appearances to the hidden structure of things. His discovery reminds us that reality is often invisible until imagination makes it visible. He proved that mathematics is not merely a language of numbers, but a lens through which the human spirit can perceive the infinite. If one were to travel back in time and stand beside him as he wrote, one might see a man absorbed in thought, his eyes distant, his fingers moving across pages filled with equations. Outside, the wind would stir the trees, and perhaps, in that whisper of air, Maxwell would hear a faint echo of the same invisible waves he was describing. He would look up, smile faintly, and return to his work, translating the music of the universe into human language. In the decades following his death, as physicists explored the implications of his theory, they came to see that Maxwell had not merely unified electricity and magnetism, he had unified knowledge itself. He showed that the boundaries between disciplines, between physics and mathematics, between experiment and theory, are artificial. True understanding lies in synthesis. His achievement stands as one of the great triumphs of the human mind, a moment when thought itself expanded the horizon of the possible. Today, when a radio transmits across continents, when a cell phone connects voices across oceans, when a telescope detects the faint glow of cosmic microwave background radiation, it is Maxwell's voice we are hearing. His equations describe those waves, those photons, those energies. Every signal traveling through the ether of modern civilization carries the imprint of his genius. Maxwell never sought fame or wealth. He once wrote that his only desire was to learn the laws of the universe and interpret them for the good of mankind. He achieved far more than he could have imagined. He gave humanity the power to command invisible forces, to shape and harness energy, to see the unity behind diversity. His work transformed not only physics but the human relationship with nature. It turned the unknown into the knowable, the invisible into the imaginable, and the abstract into the practical. And yet, perhaps his greatest gift was not his equations, but the vision that produced them, the conviction that beauty and truth are inseparable. He trusted the elegance of mathematics as a guide to reality, believing that nature herself is written in that same language. The success of his theory proved him right. When later physicists sought new laws, they too followed beauty, from Einstein's relativity to Dirac's quantum equations. Maxwell had shown them the way. As the 20th century unfolded, his unification of electricity and magnetism became the template for deeper unifications, the electroic theory, the grand unified theories, and the search for a theory of everything. Each step forward echoes Maxwell's dream, that the universe is ultimately one, bound together by simple, elegant laws. In the end, the legacy of James Clerk Maxwell is more than scientific, it is spiritual. He taught us that the world is comprehensible, that the invisible can be understood, and that reason and imagination together can reveal the cosmic order. His discovery of electromagnetism was not just an act of intellect, it was an act of faith in the unity of nature. As the camera of the mind pans across the modern world, from the glowing screens of our devices to the radio waves pulsing through the night sky, we can almost hear his equations humming beneath it all, the silent rhythm of the universe continuing its eternal song. And in that music lies the echo of one man's vision, a vision born in the solitude of thought yet destined to illuminate the entire world. Even among the giants of science, James Clerk Maxwell occupies a singular place, not merely for the discoveries he made, but for the extraordinary way in which he approached the very act of understanding. To Maxwell, mathematics was not a tool, a collection of formulas to be memorized or applied mechanically. It was a language, a lens through which the invisible structures of the universe could be seen, touched, and felt. From his earliest years, he had a profound sense that the world was built upon patterns that existed long before human recognition, eternal and unchanging. To him, the study of those patterns was both a scientific pursuit and a form of art. In his youth, Maxwell had already shown a unique ability to see relationships where others saw only separate phenomena. When he played with geometric shapes or experimented with color and light, he was not merely entertaining himself. He was training his mind to recognize symmetry, proportion, and continuity, the essential qualities of the universe itself. Those early exercises were playful, but they were also deeply formative. They taught him to translate what he saw in nature into visual and mathematical representations. Even the simplest experiment, a pendulum swinging, a prism refracting light, became an opportunity to discover underlying order. As he matured, this gift developed into a remarkable capacity for abstraction. Maxwell's genius lay in his ability to hold in his mind multiple layers of reality at once: the physical phenomenon, the conceptual model, and the mathematical description. Most scientists of his time were trained to think linearly, to move from observation to theory in a straightforward, step-by-step manner. Maxwell, by contrast, thought in dimensions and patterns. He could see a problem spatially, visualize the forces in play, and translate those visual images into equations that captured the essence of the phenomenon. His mind worked like a prism, breaking reality into components, refracting them through imagination, and then recombining them into coherent, elegant solutions. At Cambridge, Maxwell immersed himself in advanced mathematics, studying the works of Laplace, Lagrange, and Hamilton. But unlike many of his peers, who saw mathematics as a collection of techniques, Maxwell approached it as a living language. He believed that every equation could reveal something profound about the universe if interpreted with insight and imagination. To him, Numbers and symbols were not merely abstract constructs, they were the vehicles through which the hidden architecture of reality could be expressed. This approach was evident in his work on the kinetic theory of gases, where he introduced the Maxwell-Boltzmann distribution. Here, he took what seemed a chaotic system, trillions of molecules moving in random directions, and imposed order through probability and statistics. He did not rely solely on direct measurement or observation. Instead, he used mathematics to visualize patterns invisible to the eye, predicting the behavior of gases with astonishing precision. In this work, the hallmark of his method is clear. He combined rigorous calculation with intuitive understanding, connecting abstract theory to physical reality in a way no one else could. Maxwell's mathematical elegance reached its pinnacle in his work on electromagnetism. The challenge he faced was formidable: to reconcile the experimental findings of Faraday and others with a coherent theoretical framework. Faraday's lines of force were revolutionary, but they lacked formal mathematical description. Most scientists found the concept too imprecise to incorporate into serious theory. Maxwell, however, saw the brilliance in Faraday's intuition. He understood that these lines were not mere abstractions but tangible representations of physical reality. To capture them mathematically, he introduced a set of equations that described how electric and magnetic fields interact, change, and propagate through space. These equations were not simply functional, they were aesthetically pleasing, symmetrical, and profoundly revealing. One of Maxwell's greatest innovations was the introduction of the displacement current, an idea so subtle that it was almost invisible in the mathematics at first glance. By adding this term, he completed the symmetry between electric and magnetic fields, allowing for the existence of self-propagating electromagnetic waves. It was a stroke of genius that transformed our understanding of light, revealing it as an electromagnetic phenomenon. But what makes this moment truly remarkable is not the technical achievement alone, it is the way Maxwell arrived at it. He did not follow experimental data blindly. He trusted in the internal logic and beauty of the mathematics itself, believing that a consistent and elegant structure would reveal deeper truths. Maxwell's visualization techniques were integral to his mathematical work. He often imagined fields as physical entities, stretching, twisting, and vibrating in space. These were not static images but dynamic, living pictures. He could mentally simulate how lines of force would respond to a moving charge, how waves would propagate, how energy would be transferred. This ability to see equations in motion allowed him to anticipate phenomena that experiments had not yet confirmed. In essence, Maxwell's mind acted as a laboratory, where experiments were conducted in the imagination, and mathematics served as the precise language of observation. His notebooks reveal sketches and diagrams that resemble both scientific illustration and abstract art. They show field lines curling around magnets, waves rippling through space, and vortices of energy moving in patterns that are almost musical in their symmetry. To Maxwell, these visualizations were essential. They connected the abstract symbols of mathematics to the physical world. He believed that without this imaginative insight, equations would be lifeless and incomplete. It was through this interplay of imagination and calculation that he discovered the electromagnetic waves, now fundamental to modern physics. Even in more theoretical pursuits, Maxwell's approach remained consistent. When exploring the nature of color perception, he applied the same principles of visualization and mathematical reasoning. He did not merely measure the wavelengths of light, he constructed models to understand how the human eye perceives combinations of colors. Here again, mathematics was a tool not for computation alone, but for bridging the gap between physical reality and human perception. Maxwell's work in optics, like his work in electromagnetism, demonstrates that his genius lay not in any single discovery but in the consistent application of a way of seeing the world. A synthesis of intuition, imagination, and rigorous mathematics. Maxwell also understood the importance of symmetry in nature. For him, symmetry was not merely an aesthetic ideal, but a guide to truth. When he examined the laws governing electric and magnetic fields, he sought patterns of balance and correspondence. This focus on symmetry led directly to his introduction of the displacement current, completing the theoretical structure of electromagnetism. It also provided a template for future scientists to identify deeper symmetries in nature, ultimately influencing the development of modern theories such as quantum mechanics and relativity. His approach to problem solving was holistic. Maxwell did not isolate variables in the reductionist manner common among his contemporaries. He looked at systems as interconnected wholes, recognizing that behavior in one part could affect the entirety. This perspective allowed him to predict phenomena that would later be experimentally verified, such as the propagation of electromagnetic waves and the behavior of gases. In every instance, his methods combined careful observation, imaginative visualization, and precise mathematical formalism. Maxwell's influence on subsequent generations of physicists cannot be overstated. Einstein, for example, repeatedly acknowledged that his own work on relativity depended on the insights provided by Maxwell's equations. The realization that the speed of light was constant in all frames of reference, a cornerstone of special relativity, was hidden within Maxwell's formulation of electromagnetism. Maxwell, through his mathematical elegance and visualization techniques, had already paved the way for the conceptual revolutions of the 20th century. Beyond physics, Maxwell's integration of mathematics and visualization offers a profound lesson in human cognition. He demonstrates that the mind is capable of perceiving realities beyond immediate sensory experience, provided it is trained to think in abstract yet coherent patterns. By converting intuition into equations and equations back into images, he created a feedback loop in which understanding deepened with every iteration. In this way, Maxwell exemplifies the potential of the human intellect to extend beyond the tangible world into the domain of pure conceptual insight. Maxwell's notebooks also reveal a playful side to his work, one that contrasts with the intense focus of his theoretical achievements. He would experiment with mechanical models, use toys to demonstrate principles of motion and energy, and explore the aesthetic qualities of mathematical patterns. This playful engagement was not a distraction, but a source of creativity. It allowed him to approach problems from multiple angles, to see possibilities that more conventional thinkers would miss. The interweaving of rigor and imagination, discipline and play, defines the unique character of his genius. His ability to visualize physical phenomena mathematically was especially critical in the context of the 19th century, when experimental tools were limited. Laboratory instruments could measure voltage, current, and magnetic field strength, but they could not show the lines of force or the propagation of waves through space. Maxwell's equations allowed scientists to perceive what was otherwise invisible, to predict results, and to guide experiments with confidence. In effect, mathematics became a window into the unseen structure of reality, a window opened first by Maxwell. This approach also imbued his work with a sense of inevitability. Once Maxwell's equations were laid down, the consequences followed logically. Electromagnetic waves, the speed of light, the behavior of circuits, the interplay of electric and magnetic fields, all could be deduced from a single coherent system. Yet the process of discovery was not mechanical. It required a mind capable of holding abstract concepts, of seeing their dynamic interplay, and of trusting that mathematical harmony reflects natural truth. Maxwell exemplified that rare synthesis of intuition, imagination, and analytical rigor. His understanding of physical phenomena as inherently visual and geometric also extended to his work on color theory. In investigating how humans perceive colors, Maxwell combined quantitative measurements of light intensity with models that represented color interactions geometrically. He introduced the idea that any visible color could be constructed from three primary components, a principle that remains the foundation of modern color science. Here again, his methodology fused abstraction with visualization. Mathematics provided precision, while geometric models provided insight. By combining visual intuition with mathematical formalism, Maxwell was able to bridge gaps between seemingly unrelated domains: electricity and magnetism, light and optics, color perception, and mechanical motion. All were connected by the same principles of field behavior and mathematical symmetry. This integrative perspective is a defining feature of his work and a hallmark of his intellectual legacy. The elegance of Maxwell's mathematics was inseparable from its explanatory power. Each equation, while abstract, corresponded to observable reality. Changes in one variable had predictable consequences for others. Waves propagated as expected. Energy was conserved. Fields interacted according to precise rules. Yet within this rigor lay creativity, the freedom to imagine patterns, to extend concepts beyond current experiments, and to anticipate phenomena not yet observed. Maxwell's work is an enduring testament to the productive marriage of imagination and discipline. The second half of Maxwell's exploration into the elegance of mathematics and visualization deepens into a profound meditation on the nature of knowledge itself. As he refined his equations, he became increasingly aware that mathematics was more than a descriptive tool. It was a window into the underlying structure of reality. Each symbol and operation carried meaning beyond the numerical value it represented. When Maxwell wrote an equation, he was simultaneously performing an experiment, constructing a mental model, and crafting a visual narrative of invisible forces. The abstraction of mathematics did not distance him from the physical world, it connected him more deeply to it. His approach exemplified a principle rarely articulated at the time: the universe is inherently comprehensible because it is structured, and that structure can be perceived through patterns. For Maxwell, patterns were the essential language of nature. When he observed a magnetic field, he did not merely measure its strength, he imagined the lines of force stretching across space, curving, twisting, interacting. These mental images allowed him to predict behavior in new contexts, to hypothesize phenomena that no experiment had yet confirmed. His mind transformed the abstract into tangible intuition, showing that understanding comes not from rote calculation alone, but from imaginative engagement with the world. In the midst of his work on electromagnetic theory, Maxwell also confronted the philosophical implications of his discoveries. The notion that fields filled all of space challenged classical ideas of emptiness and action at a distance. Newtonian physics had treated space as a passive backdrop, a void through which forces acted instantaneously. Maxwell's vision, by contrast, proposed that space itself was active, filled with energy, and capable of transmitting interactions. Light, electricity, and magnetism were no longer isolated phenomena, they were ripples in a universal medium. This understanding transformed how scientists conceived of reality, positioning the field as a fundamental entity in its own right. Visualization played a crucial role in this conceptual shift. Maxwell's sketches reveal dynamic, almost kinetic diagrams, loops of field lines curling around currents, waves undulating through the ether, energy flowing invisibly through space. These were not artistic flourishes, they were essential cognitive tools. Maxwell could mentally manipulate these structures, turning, twisting, and extending them to explore consequences. This mental simulation allowed him to test ideas before formalizing them mathematically, bridging the gap between theory and observation in a remarkably efficient and creative way. The integration of visualization and mathematics also had profound implications for pedagogy. Maxwell's approach demonstrated that complex phenomena could be understood by aligning abstract reasoning with sensory intuition. His methods anticipated modern educational practices that emphasize conceptual modeling alongside quantitative analysis. By thinking in terms of fields and lines of force, students could grasp invisible interactions that would otherwise remain abstract. Maxwell had, in effect, created a framework for understanding the unseen, a framework that remains central to physics education today. Maxwell's insights extended beyond electromagnetism. In his work on kinetic theory, he treated the chaotic motion of molecules as a system of statistical distributions. By introducing probability into physics, he transformed the way scientists approached uncertainty and complexity. Just as he visualized electromagnetic fields as continuous structures, he imagined the invisible dance of molecules as a flowing, dynamic network. The connection between visualization and abstraction is clear. Maxwell's imagination allowed him to perceive order where others saw randomness, to translate complexity into comprehensible structure. In color theory, Maxwell's approach was equally groundbreaking. He recognized that human perception of color could be mapped onto 3 dimensions corresponding to the 3 primary colors. By combining mathematical precision with geometric representation, he created a model that could predict how different wavelengths of light would be perceived when combined. This work not only advanced the science of optics, but also influenced practical applications in art, photography, and printing. Once again, his genius lay in bridging abstract mathematics with tangible human experience. Maxwell's commitment to elegance and coherence in mathematics was more than aesthetic, it was a methodological principle. He believed that nature's laws were inherently simple, harmonious, and symmetrical, and that the role of the scientist was to uncover that underlying simplicity. When he formulated the displacement current, he did so not to fit experimental data, but to complete the logical symmetry of the theory. This act of intellectual intuition, trusting in the inherent beauty of the system, demonstrates the deep interplay between creativity and rationality in scientific discovery. His method of visualizing physical phenomena also contributed to predictive power. Maxwell could foresee electromagnetic waves before they were experimentally confirmed, radio waves decades before Hertz demonstrated them in the laboratory. He could deduce the behavior of light from the properties of electric and magnetic fields. These predictions were not mere guesses, they were consequences of a deeply coherent mathematical framework, supported by mental simulations that allowed him to see the results before performing experiments. This combination of visualization and calculation exemplifies the power of imaginative reasoning in science. Maxwell's notebooks reveal another dimension of his genius, the playful exploration of concepts. He often approached problems as if experimenting with puzzles or toys, exploring variations and considering what-if scenarios. This playfulness was not trivial, it enabled him to think beyond conventional constraints, to consider connections that might otherwise be overlooked. Creativity and rigor, intuition and calculation, imagination and mathematics, Maxwell wove these elements together seamlessly, creating a methodological tapestry that allowed him to explore new frontiers of understanding. The mental images he constructed were also deeply spatial. Maxwell's equations are often represented in vector form, describing fields as quantities with magnitude and direction. This spatial conception allowed him to imagine the dynamic interplay of electric and magnetic effects in 3 dimensions. Unlike many contemporary scientists who relied solely on algebraic manipulation, Maxwell's thought experiments were inherently geometric. He could mentally rotate, stretch, and bend field lines, predicting their interactions as if conducting experiments within the mind itself. This approach anticipates modern computational methods where visual simulation complements analytical work. One of the most profound outcomes of Maxwell's visualization techniques is their role in unifying different domains of physics. His understanding of fields provided a common language for electricity, magnetism, and light. By conceptualizing interactions as waves propagating through a medium, he created a framework that could accommodate disparate phenomena under a single theoretical umbrella. Later developments in physics, from relativity to quantum field theory, would build upon this foundation. Maxwell's approach demonstrates that the ability to visualize abstract structures is not merely an intellectual luxury. It is essential for synthesizing knowledge across domains. Maxwell's work also illustrates the importance of intuition in scientific discovery. He often relied on a sense of mathematical beauty to guide his reasoning. If an equation seemed elegant and symmetrical, he trusted that it was on the right path. Conversely, If a formula felt forced or inconsistent with the overall pattern, he revised it. This reliance on aesthetic judgment is a recurring theme in the history of science, but Maxwell's application of it was unusually rigorous. By combining intuition with empirical grounding, he ensured that his insights were both imaginative and accurate. The interplay of imagination and mathematics in Maxwell's work has profound implications for the philosophy of science. It challenges the notion that knowledge emerges solely from observation and experimentation. Instead, it suggests that cognitive structures, mental models, visualizations, and abstract reasoning play a critical role in discovery. Maxwell's equations did not arise purely from measurement. They arose from the creative synthesis of observed patterns, mental imagery, and mathematical formalism. In this sense, his work exemplifies a deeply human mode of cognition, one in which imagination and intellect are inseparable. Maxwell's ability to connect visualization with mathematics also had practical consequences. By representing electromagnetic phenomena as waves in a continuous medium, he provided engineers and physicists with tools for design and prediction. Circuits could be analyzed, light could be manipulated, and electromagnetic radiation could be harnessed long before modern instruments existed. His theoretical vision preceded technological realization, demonstrating that abstract understanding can drive practical innovation. Even in personal correspondence, Maxwell revealed the aesthetic dimension of his scientific thought. He frequently remarked on the beauty and harmony of equations, often comparing their elegance to musical composition. This aesthetic sensitivity was not mere ornamentation, it guided the structure of his theories, suggesting symmetries, constraints, and relationships that might otherwise remain hidden. By attending to beauty as well as correctness, Maxwell developed a methodology that combined analytical rigor with creative insight. His approach remains instructive for contemporary science. In an era dominated by computational power and experimental instrumentation, Maxwell's integration of visualization and mathematics offers a timeless lesson. Understanding is not merely about numbers, measurements, or graphs, it is about constructing coherent mental models that make sense of complexity. Visualization, in this context, is a bridge between intuition and formalism, enabling scientists to navigate the unknown with confidence and creativity. Moreover, Maxwell's work highlights the role of human perception in the discovery process. By imagining phenomena beyond the reach of the senses, he expanded the horizon of what could be known. Fields, waves, and invisible interactions became accessible to thought through the synthesis of visualization and mathematics. This method anticipates modern theoretical approaches, from quantum mechanics to cosmology, where phenomena often lie far beyond direct sensory experience. Maxwell's mathematical elegance and visualization techniques also fostered unification across diverse areas of physics. Electricity, magnetism, light, color, and kinetic theory were no longer isolated subjects, they became interconnected manifestations of underlying principles. This holistic perspective enabled him to predict new phenomena, suggest experiments, and provide conceptual clarity in a rapidly developing field. His legacy demonstrates that the power of science lies not only in measurement, but in the imagination and creativity that underpin discovery. In the end, Maxwell's brilliance was not merely in producing equations or confirming theories. It was in perceiving the invisible patterns that govern reality and translating them into language, images, and symbols comprehensible to the human mind. By doing so, he created a foundation on which modern physics rests. He taught that the unseen universe can be understood, not by brute measurement alone, but by the harmonious interplay of mathematics, visualization, and intuition. Maxwell's work remains a testament to the capacity of human cognition. It reveals that the universe, though vast and complex, is ultimately intelligible. Through imagination guided by mathematical discipline, one can perceive connections invisible to the eye and anticipate phenomena beyond immediate experience. His legacy is both practical and inspirational, practical in the technologies and scientific frameworks it enabled, and inspirational in demonstrating the heights of human thought and the depth of intellectual vision. Maxwell's integration of mathematics and visualization continues to influence contemporary physics. From computational modeling to the visualization of quantum fields, scientists rely on the principles he exemplified: abstract reasoning paired with intuitive understanding, symmetry guiding theory, and mental imagery informing formal analysis. In this sense, Maxwell was not only a scientist of his own era, he was a visionary whose methods resonate through the entire trajectory of modern science. The story of James Clerk Maxwell is not simply a tale of equations and discoveries. It is the story of a mind that reshaped humanity's understanding of the physical universe. His work on electromagnetism did more than unify previously separate forces. It laid the foundation for an entirely new era of physics, one in which the invisible threads of energy and force could be understood, predicted, and eventually harnessed. Before Maxwell, electricity and magnetism were studied largely as isolated phenomena. Scientists could measure the pull of a magnet, the spark of an electric current, or the behavior of light, but the underlying unity of these forces remained hidden. Maxwell revealed that these disparate elements were part of a single, coherent system, a revelation that would transform science forever. His equations, elegant and precise, showed that electric and magnetic fields were intertwined, generating waves that could propagate through space at a fixed speed. These waves, Maxwell concluded, were identical to light itself. In this realization, the nature of light was no longer a mystery. Light was not a substance, a particle, or a simple vibration in an unspecified medium. It was a dynamic manifestation of the electromagnetic field, a ripple in a universal continuum that connected all points in space. This insight bridged the gap between physics and optics, between theory and observation, and provided the first rigorous understanding of one of the most fundamental aspects of reality. Maxwell's work also anticipated technological revolutions that would transform the modern world. The theoretical prediction of electromagnetic waves laid the groundwork for radio, television, radar, and wireless communication. Decades after Maxwell's death, Heinrich Hertz would experimentally generate these waves, confirming Maxwell's predictions and demonstrating the practical relevance of his abstract theory. What began as an intellectual pursuit became the foundation for a technological infrastructure that reshaped global communication and industry. In this sense, Maxwell was not only a scientist, he was a visionary whose ideas reached far beyond the laboratories of his time. The impact of Maxwell's work on physics was profound. By introducing the concept of the electromagnetic field, he shifted the framework of understanding from particles acting at a distance to a continuum filled with dynamic forces. Space itself became active, a medium in which energy could propagate, interact, and transform. This reconceptualization was essential for the later development of relativity and quantum theory. Einstein, for example, acknowledged the centrality of Maxwell's equations in his own work. The constancy of the speed of light, a cornerstone of special relativity, was embedded within Maxwell's formulation. In this way, the vision of a single physicist in 19th-century Scotland paved the way for the most revolutionary ideas of the 20th century. Maxwell's influence extended beyond theoretical physics to the philosophy of science. He demonstrated that the universe could be understood as an interconnected whole, governed by universal laws that could be expressed mathematically. The power of abstraction, coupled with imaginative visualization, allowed him to perceive structures invisible to the senses. His approach taught generations of scientists that understanding does not emerge solely from observation, but from the interplay of thought, intuition, and formal reasoning. The electromagnetic field became both a practical tool and a conceptual lens, revealing the hidden order underlying apparent chaos. In addition to its scientific significance, Maxwell's work has a human dimension. His vision reflects a mind capable of profound creativity and insight, one that combined rigorous logic with imaginative exploration. He demonstrated that mathematics is not merely a tool for calculation, but a way to perceive the universe itself. By visualizing the dynamics of fields, waves, and energy, Maxwell was able to anticipate phenomena before they were observed, showing that the human mind can extend its reach beyond immediate experience. The electromagnetic era that Maxwell ushered in transformed everyday life. Electricity, wireless communication, lighting, and modern electronics all rely on principles he elucidated. His work also inspired new generations of scientists, setting the stage for quantum mechanics, relativity, and the unification of fundamental forces. Maxwell's equations remain central to physics, engineering, and technology, serving as a bridge between abstract theory and tangible reality. Ultimately, Maxwell's impact lies not only in the discoveries themselves, but in the vision they represent. He revealed the deep unity of nature, showing that the forces that govern the cosmos are interconnected, predictable, and comprehensible. His insights transformed the way humans perceive the physical world, turning mystery into understanding and possibility into reality. Through his work, Maxwell demonstrated the power of thought, imagination, and mathematics to illuminate the hidden structures of the universe, leaving a legacy that continues to shape science, technology, and human understanding more than a century after his death. James Clerk Maxwell's contributions to science did not end with his own discoveries. They rippled across generations, shaping the very foundation of modern physics and technology. His work on electromagnetism, his elegant mathematical formulations, and his imaginative approach to visualizing unseen phenomena created a framework that continues to influence the way humanity interacts with the universe. Maxwell was not merely solving problems of his time, he was constructing a bridge between abstract thought and tangible reality, a bridge that would carry future scientists and innovators into uncharted territories. One of Maxwell's most profound legacies lies in the concept of the electromagnetic field. Before Maxwell, electricity and magnetism were considered separate forces, each with its own rules and behaviors. Experiments showed interactions between them, but no unifying principle existed. Maxwell's genius was to see beyond the surface, to understand that these phenomena were manifestations of a single underlying system. By formulating his four elegant equations, he revealed the dynamic interplay between electric and magnetic fields, showing that a changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. From this simple but powerful principle emerged the realization that light itself is an electromagnetic wave, traveling through space at a fixed speed. This unification not only explained the nature of light, but also paved the way for the entire field of modern physics. The implications of Maxwell's work extended far beyond theory. By predicting the existence of electromagnetic waves, he laid the foundation for technologies that would revolutionize human life. Decades later, Heinrich Hertz's experiments confirmed these waves, demonstrating that they could be generated, transmitted, and detected. This discovery became the backbone of wireless communication, leading to radio, television, radar, and eventually the Internet. In a very real sense, every modern device that transmits or receives information owes its existence to Maxwell's vision. His equations made the invisible tangible, showing that energy could move across empty space and be harnessed for practical use. Maxwell's legacy also includes the profound influence he had on future theoretical developments. Albert Einstein, when developing the special theory of relativity, relied heavily on Maxwell's equations. The constancy of the speed of light, embedded within those equations, became a cornerstone of Einstein's revolutionary understanding of space and time. Similarly, Maxwell's ideas about fields and waves influenced the development of quantum mechanics and quantum field theory, shaping our understanding of particles, forces, and the fundamental nature of reality. In this way, Maxwell's work became a keystone, connecting classical physics to the discoveries of the 20th century and beyond. Beyond the realm of physics, Maxwell's approach to scientific inquiry remains inspirational. He demonstrated that the power of human thought lies in the combination of imagination, visualization, and rigorous mathematics. By mentally simulating the behavior of fields and waves, he could predict phenomena that had not yet been observed. His ability to see the invisible, to translate abstract concepts into precise mathematical language, exemplifies a model of creativity and reasoning that transcends time. Scientists today continue to employ similar methods when exploring phenomena that are too small, too fast, or too distant to observe directly. Maxwell showed that the mind itself can serve as a laboratory where theory and intuition converge to reveal truths hidden from immediate perception. The broader impact of Maxwell's work is visible in nearly every aspect of modern life. Electricity powers homes and cities, wireless communication connects people across continents, medical imaging and radar technologies rely on principles he elucidated. Yet his influence is not limited to applications, it reshaped our understanding of the universe. Space is no longer seen as empty, it is a medium filled with dynamic fields, energy, and potential. Light is no longer a mysterious phenomenon, it is understood as an electromagnetic wave, fully integrated into the continuum of physical forces. Maxwell provided humanity with a conceptual lens, allowing us to perceive connections where previously we saw only isolated events. Maxwell's legacy is also a testament to the interplay between science and philosophy. By revealing the underlying unity of nature, he showed that seemingly disparate phenomena are part of a coherent system. This insight has implications beyond physics, suggesting that the universe is intelligible and that the pursuit of knowledge is both possible and rewarding. Maxwell's vision reflects a profound faith in the order and beauty of nature, a conviction that guides the scientist to look beyond appearances and seek deeper patterns. Finally, Maxwell's influence is cultural as well as scientific. His life and work exemplify the ideal of the visionary scientist, disciplined, imaginative, and fearless in pursuing understanding. His equations are celebrated not only for their predictive power, but for their aesthetic elegance, a fusion of clarity, symmetry, and insight. This combination of intellectual rigor and beauty has inspired generations of physicists, engineers, and mathematicians to explore the universe with curiosity and creativity. Maxwell's legacy reminds us that science is not merely a collection of facts, but a creative endeavor in which imagination, insight, and mathematics converge to reveal the profound order of the cosmos. In conclusion, Maxwell's impact on science and technology is immeasurable. By unifying electricity, magnetism, and light, he laid the foundation for modern physics. By combining mathematical rigor with imaginative visualization, he provided a model for creative scientific thinking. By predicting phenomena before they could be observed, he demonstrated the power of insight and intuition. And by revealing the deep unity of nature, he transformed humanity's understanding of the universe. Maxwell's vision continues to illuminate the path of discovery, shaping the way we perceive, interact with, and harness the forces of the world around us, leaving a legacy that endures in both knowledge and imagination. James Clerk Maxwell's work represents a turning point in the history of science, a moment when human understanding leaped beyond the limits of direct observation into the realm of profound abstraction and insight. By formulating his famous equations, he not only unified electricity and magnetism, but also provided a mathematical and conceptual framework that revealed the universe in a new light. His vision was one in which invisible forces could be comprehended, predicted, and applied, laying the groundwork for the technologies and scientific paradigms that define the modern world. At the core of Maxwell's achievement is the realization that electric and magnetic phenomena are deeply interconnected. Before Maxwell, scientists studied electricity and magnetism largely in isolation. Experiments revealed correlations, such as the deflection of a compass needle by a current, but no unifying principle explained these observations. Maxwell saw the underlying order. Electric fields and magnetic fields are two aspects of a single reality, interdependent and dynamic. By representing this relationship through four elegant equations, he captured the behavior of these fields and their interactions with astonishing clarity. These equations not only described what had been observed, They predicted what had not yet been seen, most notably the existence of electromagnetic waves. The prediction of these waves was one of Maxwell's most visionary contributions. His equations implied that a disturbance in an electric field would generate a magnetic field, which in turn would regenerate the electric field, creating a self-propagating wave traveling through space. Crucially, Maxwell calculated that these waves moved at a speed corresponding exactly to the speed of light, leading to the profound insight that light itself is an electromagnetic phenomenon. This realization unified optics with electromagnetism, revealing that light, radio waves, and other forms of electromagnetic radiation are governed by the same underlying principles. Maxwell had, in effect, described the invisible architecture of the cosmos. Maxwell's vision extended beyond theoretical elegance. By demonstrating that electromagnetic waves could exist and propagate through space, he laid the foundation for technologies that would transform human society. Hertz's experiments, decades later, confirmed these waves, showing that they could be generated and detected in the laboratory. This breakthrough led directly to the development of radio, television, radar, and modern wireless communication. Every device that transmits or receives information, from radios and televisions to smartphones and satellites, operates according to principles Maxwell articulated in the 19th century. His equations are the blueprint for a world that, in his own time, could barely be imagined. Beyond technological implications, Maxwell's work had profound consequences for theoretical physics. By introducing the concept of the electromagnetic field, he shifted the understanding of forces from particles acting at a distance to continuous interactions across space. Space itself became an active medium filled with energy capable of transmitting forces. This conceptual leap laid the groundwork for Einstein's theory of relativity, in which the constancy of the speed of light, encoded in Maxwell's equations, becomes a fundamental principle. The transition from classical to modern physics, from the deterministic world of Newton to the relativistic and quantum universe, owes a deep debt to Maxwell's insights. Maxwell's methodology was equally revolutionary. He combined rigorous mathematics with vivid mental visualization, imagining the dynamic behavior of fields and forces in space. He could mentally trace the lines of force around magnets, visualize the propagation of waves, and anticipate the interactions of electric and magnetic fields. These mental images were not mere illustrations, they were central to his problem-solving process. By merging imagination with mathematical precision, Maxwell demonstrated that human cognition is capable of extending beyond the limits of direct perception. He made the invisible tangible through thought, providing a model for scientific creativity that remains relevant today. His work also emphasized symmetry and coherence in nature. Maxwell sought patterns and balance in his equations, ensuring that they reflected the harmony inherent in physical laws. This aesthetic principle guided his reasoning, leading him to introduce concepts such as the displacement current to complete the theoretical framework. By trusting in the internal logic and elegance of his system, Maxwell anticipated phenomena before experimental verification. This approach underscores a central lesson of his work, that understanding the universe requires not only observation, but also imaginative reasoning guided by mathematical beauty. Maxwell's influence extends across multiple domains of science and technology. Electromagnetism is central to electrical engineering, telecommunications, optics, and modern electronics. His concepts of fields and waves underpin quantum mechanics and field theory, shaping our understanding of particles and interactions at the most fundamental level. In every case, Maxwell's equations serve as a bridge between abstraction and application, allowing theoretical insight to inform experimental design and practical innovation. Moreover, Maxwell's achievements highlight the human capacity for insight. By visualizing invisible structures, translating them into mathematics, and trusting the harmony of nature, he revealed a universe that is coherent, comprehensible, and profoundly interconnected. His work demonstrates that discovery is as much an act of imagination as of calculation. that the mind itself can explore realms inaccessible to the senses, and that rigorous reasoning and creative insight are inseparable in the pursuit of knowledge. In the modern world, the legacy of Maxwell is everywhere. Wireless communication, medical imaging, satellite technology, and even our understanding of light and radiation all trace their roots to his vision. But beyond practical applications, Maxwell's work embodies a philosophical truth that the universe, no matter how vast or complex, is structured in a way that can be understood through human thought. By revealing the unity of electric and magnetic phenomena, by predicting waves that traverse the cosmos, and by demonstrating the power of visualization paired with mathematics, Maxwell transformed the human conception of reality itself. In essence, Maxwell's sixth keynote reminds us that scientific progress is not merely the accumulation of facts, but the expansion of perception. Through his equations, his imagination, and his insight, Maxwell allowed humanity to perceive the invisible, to anticipate the unseen, and to harness the forces of nature in ways previously unimaginable. His vision continues to illuminate science, technology, and the imagination, a testament to the enduring power of thought guided by rigor, creativity, and profound understanding. James Clerk Maxwell's journey through the landscapes of physics and mathematics culminates in a vision that transformed not only the way humans understand the universe, but also the very tools and methods by which we explore it. His work was not confined to isolated discoveries. It was a holistic enterprise, a synthesis of imagination, observation, and mathematical rigor that revealed the hidden architecture of reality. Maxwell's genius lay in seeing the invisible, in translating abstract concepts into tangible forms, and in bridging the gap between the physical and the conceptual, leaving a legacy that continues to shape science today. At the heart of Maxwell's vision is the unification of seemingly disparate phenomena. Electricity, magnetism, and light, once thought separate and unrelated, were brought together under a single theoretical framework. His equations demonstrated that electric and magnetic fields are not independent entities, but components of a dynamic, interrelated system. By showing that variations in these fields could propagate as waves through space, Maxwell revealed that light itself is an electromagnetic wave. This insight did more than solve a scientific puzzle. It fundamentally changed humanity's understanding of nature. Suddenly, forces that had been mysterious and intangible became comprehensible, predictable, and elegantly unified. Maxwell's insight extended beyond equations. It encompassed the methodology by which science could progress. He demonstrated that understanding comes not only from experimentation, but also from visualization, intuition, and abstraction. He could mentally trace the lines of force around magnets, visualize the ripple of electromagnetic waves through space, and predict their behavior before performing experiments. These mental simulations were not mere aids to calculation. They were central to his creative process. Maxwell's work exemplifies how the human mind can extend its reach, perceiving patterns and relationships that lie beyond immediate sensory experience. The predictive power of Maxwell's work is one of its most remarkable aspects. By formulating his equations, he anticipated phenomena that would not be observed until decades later. Radio waves, the behavior of light, and the transmission of electromagnetic energy across space were all outcomes of his theoretical insight. These predictions eventually became the foundation of technologies that transformed human life, from wireless communication to medical imaging and global navigation systems. Maxwell's ability to foresee practical applications from abstract theory highlights the profound interplay between imagination and scientific rigor in his work. Maxwell's vision also had a deep philosophical dimension. He shifted the scientific perspective from a particle-centered, mechanical view of the universe to one in which fields and interactions are fundamental. Space itself became an active medium, capable of transmitting energy and mediating forces. This reconceptualization laid the groundwork for future developments in relativity and quantum field theory. By emphasizing the interconnectedness of natural phenomena, Maxwell showed that the universe is coherent, ordered, and intelligible, a system that can be understood through both observation and reasoned abstraction. Equally important was Maxwell's attention to elegance and symmetry. He believed that the laws of nature would reveal themselves in forms that are balanced, harmonious, and aesthetically satisfying. This principle guided him in introducing innovations such as the displacement current, ensuring that the equations describing electromagnetism were complete and consistent. Maxwell's reliance on mathematical beauty as a guide to truth demonstrates that intuition, creativity, and aesthetic judgment can play as critical a role in discovery as empirical measurement. His approach offers a timeless lesson. The universe may be understood not only through experimentation, but also through the disciplined cultivation of insight, imagination, and elegance in thought. Maxwell's influence extends far beyond the 19th century. Albert Einstein credited Maxwell's equations as central to the development of special relativity, while the advent of quantum theory built upon the concept of fields he had pioneered. Modern physics, engineering, and technology continue to rely on principles he articulated more than a century ago. From smartphones and satellites to lasers and fiber optics, Maxwell's vision remains embedded in the foundations of contemporary life. In this sense, his work is both timeless and transformative, bridging the conceptual and the practical, the abstract and the tangible. Beyond practical applications, Maxwell's legacy inspires the human imagination. His ability to visualize invisible phenomena, to translate complex ideas into elegant mathematics, and to anticipate the unseen demonstrates the extraordinary potential of the human mind. Science, as Maxwell practiced it, is not a dry collection of facts, it is an art form, a creative enterprise in which intuition, logic, and imagination converge. By studying Maxwell's work, generations of scientists have learned that discovery is as much about vision and insight as it is about measurement and calculation. Maxwell's life also exemplifies the virtues of curiosity, perseverance, and intellectual integrity. He pursued knowledge not for fame or recognition, but out of a profound desire to understand the natural world. His notebooks reveal a mind constantly exploring, questioning, and seeking connections. Experiments, mental simulations, and mathematical reasoning were intertwined in his method, each reinforcing and expanding the other. This integrative approach allowed him to perceive the unity underlying apparent diversity, to synthesize insights across domains, and to reveal patterns invisible to his contemporaries. Ultimately, Maxwell's seventh keynote reminds us that scientific achievement is not merely about solving problems, it is about transforming perception. By unifying electricity, magnetism, and light, by visualizing the unseen, and by trusting in the harmony and symmetry of nature, Maxwell expanded humanity's capacity to understand, predict, and shape the universe. His work shows that science is a human endeavor, grounded in curiosity, imagination, and disciplined thought, capable of illuminating both the world around us and the potential within us. Maxwell's vision endures because it combines discovery with insight, abstraction with application, and imagination with rigor. He revealed a universe that is coherent, comprehensible, and interconnected, offering a lens through which generations of scientists and thinkers can explore reality. His legacy is a testament to the transformative power of one mind, capable of perceiving what is unseen, unifying what appears separate, and inspiring humanity to look beyond the immediate and embrace the profound possibilities of understanding. In every wave of light, every signal transmitted across space, and every insight into the forces of nature, Maxwell's presence endures, a guiding vision of intellect, creativity, and scientific imagination.